thank God I thought we have only 1 week. In fact, we have 2 weeks. Or? Yeah. Yes. Thank you. Sit down, sit down. Sit down. You are in the class, I am teaching. Okay. Anyways, it's not a new topic, it's related to signal design, which we did earlier. The thing which we did earlier was cycle length calculation. Okay, these are how we divide the cycle length. Okay, so we have discussed different types of signals earlier. Signals can be operated in different ways. One of those is pre-time signals. Okay, where the timing is fixed. Okay, we have a signal which has fixed timing. Okay. The other one is called actuated. The other types are actuated. Does anyone remember what is the difference between this one and actuated? Actuated means what? If a signal does not have fixed timing, then how does it work? If I don't fix the timing of the signal, then how will it work? By sensors. Okay. So, but those timings which are with sensors, they are more complicated because you are not designing for one value, you are designing for a range of values. Okay. So, then the calculation will be more, and you probably would need a software to do it for you. Okay, because then it will become an optimization problem. Okay, there is a course in optimization. Anybody has taken that? For the elective course. Operational research. No one? On. It was taught the last semester. Okay, anyways. The point is we are doing pre-time signal design. Okay, pre-time signal design has 3 main steps or 3 main phases, and then each phase is divided into multiple steps. The first phase is you develop a phasing plan. Okay, sorry for the diagrams. It's time to be color. That's the value. We have to zoom in now. Anyways.
It's good.
Very nice. You don't understand anything. Huh? This is what AI does. Okay? In the morning, there was a presentation. In the afternoon, there was a presentation. So in the morning, there was people were giving presentation, and there was slides coming up. So they were struggling to read what is on the slide. Okay. So I told them if you replace this word with this one and this word with this one, it will become easier. For example, the AI says civil engineering practitioner. What is a simple word for it? What is a civil engineering practitioner? Who is a civil engineering practitioner? So easy, right? There were 3 guys. I told all 3 of them to read it. Okay? And they were struggling. Okay? I told them if you didn't take the help of AI, you would simply write engineering. If you have to write it yourself, you write. It is good for engineers. But the AI says it is blah blah blah, blah 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 for civil engineering practitioners. Okay? And yes, they could not read blah blah and stuff like that. Whatever was before that. Anyways. So this is what happens. The last time I took the help of AI, literally. Anyways. The first phase, the first activity in signal design is a phasing plan. Phasing plan means what? group of movements which will move together. Okay, so that is one phase. The movements which move together from the intersection, they constitute one phase. Okay, so a phasing plan means you will make multiple groups and you will decide about their sequence. Okay, so the first group will be from east, straight and left. The second group will be from west, straight and left. Okay, the third group will be north and south straight only. And then the fourth group will be north and south left turning only. Okay, so this is what now? A phasing plan. Because I am telling you which movements will go together and in what order. This is called as a phasing plan. So you need to decide that because there can be multiple combinations. Okay, I just told you there can be different combinations. You can have straight and left, you can have two straights, you can have two lefts, okay, and so on and so forth. Then, once you have decided the phasing plan, on the basis of the movement in each phasing plan, you calculate the timing required by the device to move from this phase. Okay. Now, each phase has 3 timings. Okay. But before you go into the timing, you need to find out the time should be according to which volume. Okay. So in one phase we have different movements, right? Okay. So each movement will have its own volume. We will not have same number of vehicles going straight and left. Okay. And there can be multiple lanes for one movement. So I don't have to design for the whole movement, I have to design for one lane. Okay. Because the other lane is together, right? So if there are 3 lanes, I have to decide which lane I am designing for. And for that lane, I will need the volume. Okay. So after the phasing plan, you decide the lanes for which you are designing critically. You call it critical lane. Okay, yes, right. Do something else. Critical lane. Okay. And for that critical lane, you need the critical lane volume. Okay. So all the rest of the calculations are critical for critical lane volume. The remaining volume is negligible. You can ignore it. Okay. So what do we do with the critical lane volume? First of all, you have to find out the loss time. You have to find out, but the time is divided into different intervals. Okay. One of the timings you need is the loss time. Okay. This is what we discussed in the previous slides as well. Loss time can be startup loss time, it can be clearance loss time. Okay. When the signal opens, the drivers take some time to get moving, right? That is startup loss time. Clearance loss time is what? All finished? Finish the queue? All finished? This is startup loss time. Now got clearance loss time. Clearance loss time. Clear what? Clear the? Not the name. Clear the intersection. Clear the intersection. Okay. So when can you clear the intersection? You have to block all movements. Only vehicles which are in the intersection are moving. So for the signal it is lost. Okay, because entry is closed. Okay. So you calculate the loss times for each lane, it can be different. Okay. And then you find out the yellow time and all red time. Okay. Yellow and all red have fixed equations. You can find out yellow and all red depending upon loss times and intersection space, intersection size. Okay. Then once you have done that, we calculate the cycle length. Okay. We have calculated cycle length earlier. So whatever you need in that equation, you must have it. In that equation, we need critical volume, we need loss time, we need phases. So all these things will be there. Now we move on to the cycle length. Clear? Okay. Then after you find out the cycle length, you find out the total green time. Okay, what is total green time? You have lost time and you have the full cycle length. From the full cycle length, you subtract the lost time. This is your full green time. Okay, clear? And then you divide this green time into different phases. Okay, you divide the green time into different phases. Okay, now each phase has its own critical volume, right? So the logic says what? If phase A has more volume, it should have more what? More green time, right? Right? So this is how we divide it. On the basis of ratio of the volume it has. Okay, I have total 100 seconds of green time. Phase A has 60% of the total volume. Phase A will have 60% of the time. Clear? Okay. Then the next phase. So once you have calculated the green time, you are done with the signal design for the vehicles. Okay. The next item in the process is to check for the pedestrians. Okay, the pedestrians will cross the road. Are you providing them enough parallel green time? Parallel. Okay, so if the pedestrian is going in this direction, he needs green time there for these vehicles. Fine. So first of all, you find out how much time the pedestrian needs. The pedestrian need is depending upon his speed and what? I want to calculate how much time the pedestrian needs to go from one place to the other.
Distance.
I need the distance and the speed. You are saying something else. You take 85% down. See, now they will do it for you, their project. They have seen it. They will do it. What's your problem? You are doing project with Baba. You shouldn't have any problem. Anybody does anything, you should have any problem.
How they speak for?
I know.
Perception action, okay, I can drawing or
Perception action, okay.
for the driver, but I didn't know that for pedestrian.
Everything is okay. Oh, no problem. And she survived about 85%. They had 1 hour discussion with me about 85%. From where will we get it? Different series of getting 85%. See?
We didn't consider this speed. We considered
Whatever.
I didn't know there is speed. How we calculate the speed for everyone?
See, you came from the other here, right? This is 85%. She came from somewhere else. So this is 15%. Get it? Anyways, the point was we need the speed and we need the distance. Okay? We keep things simple here. Okay. So first of all, you calculate how much time the pedestrian needs. Then you check, because you already calculated the green time. So you check if this time is enough for the pedestrian. Okay? It should be, the green should be more than what the pedestrian needs. Right? If it is not, then you will do the adjustment. If it is equal or more, just leave it and you move on. But you have to do it for each phase. You have to do it for each phase. And usually the pedestrian timing, because you can have a phase for left turning, right? Okay? So I am the pedestrian and I have to cross. Okay? And there is a green signal here. And this green signal could be for straight, could be for left. Okay? So which timing you will check for this pedestrian? Usually the straight one. Okay? The straight time. So in every direction, you will see the straight movement, the green on the straight movement, you check it against the pedestrian line. If there are more phases, you get more phases for safety or for some other reason. If the straight green time is enough, we can move on. Okay? See? Simple. Okay. Yeah. So the first step was developing the phasing plan. In developing the phasing plan, the first and foremost thing is we are putting the signal to avoid conflicts. Okay, to avoid crashing on the beam. Okay. So the first thing, the first rule of the phasing plan is when you are combining the movements, you cannot combine conflicting movements. Simple. Okay. Clear? Logical. Okay. The second thing is one very extreme version of the phasing plan can be if I have 8 movements or 12 movements or whatever number of movements, I'll put one phase for every movement. So every movement is different. It has its own green time and yellow time. Okay? But with each phase, we have lost time. Okay? I told you there are 2 lost times, right? What? Start of effect. So when you increase the number of phases, you are increasing the number of lost times as well. Okay, so if I have 4 phases, I have 4 sets of lost times. If I have 6 phases, then I have 6 sets of lost times. Okay, so increasing the number of phases may increase safety, but it will reduce the capacity of the signal. Okay, you have to keep this in mind. There could be some local standards which you need to follow. For example, we have the right hand drive. Right? So, if we are taking the right turn on most of the signals, the right turn is open. Okay, so these are local rules and regulations to follow. Okay, so you need to follow them. Okay, with the phasing plan, you may have to design the signs and markings and the lanes of the signal as well. So the intersection design and we call it the furniture, the accessories, whatever you want to call it, the other items which you have, okay, they should be according to the phasing plan. For example, if you have a separate phase for left turning, then you also need what? To separate the lanes, right? That means you also need a separate lane for left turning. You cannot have a combined lane for left turning and keep a separate phase for left turning. It's not possible. Okay, the lane has straight and left, and the signal is only showing left. So that lane cannot be used. Okay, and then the signal itself. If there is a separate signal for left turning, I should see a separate light, which is only for left. Right? So you need the marking, you need the lane, you need the signal, okay, and then you may need the direction as well, show people where you can go and so on. Okay, so another thing is the phasing plan should be according to the volume and speed. Okay, there are 2 important items here. Heavier movements and faster movements are better to be kept separate than other movements. Especially if you have one heavy movement and one very light movement, or one heavy movement when one movement which is very fast and the other movement is very light or very slow. Okay, and combining them can be counterproductive. Okay, so usually we keep the heavier movements together. If you have to make them together, if it is possible, if they are not conflicting, then you can keep them together and the light movements together in one phase. That is more productive. Okay. If it is not possible, then the heavier movements each heavy movement may have its own phase without combining with any other movement. Okay. And you have to look into the pedestrian crossing requirements. Okay. Once you have developed the phasing plan, there are 2 types of diagrams which you can use to show the phasing plan. Okay, I need to show the phasing plan to the design engineer, to the people who are working on the field, and so on and so forth. So these diagrams are called as phase diagram and a ring diagram. So there is a phase diagram and there is a ring diagram. Ring diagram is more common. Most of the softwares show you the ring diagram. Okay, so that's why it's more common. But a phase diagram is easier. So phase diagram is what? A symbol. All movements which are happening in one phase, they are together. Okay. What is a ring? So you may have a movement from this side and you may have a movement from the opposite side, and they can be together. Okay. But can I use the same signal to indicate green for both of them? Okay. So each signal is called a ring. Why? Because each signal has the 3 lights, right? And these lights are repetitive, right? You go from green to yellow to red, and then red to yellow, and so on. Okay? So each signal has a ring of lights. Okay? So a ring diagram is showing the movement by each ring at a time, not each phase. So each phase may have more than one rings in it. Right? Okay? Before we go look at the diagrams, these are some of the legends or some of the notations we use. So you see the arrows showing the direction. Okay? You see the arrows can be from the same line, or they can be from different lines. Okay? So different lines mean different lanes. Okay? You guys call those as lines as well, right? The road has 3 lines, 4 lines. The lanes, what I call it as lanes. I've heard some of the students say the road has 3 lines. Yeah, cut that you translate it to English. Then you say line. Yes. Anyway, so the point is, different lines means different lanes. Same line means same lanes, even if they are different. Okay. So this one shows a combined lane for 3 movements, and this one shows 2 lanes. One is only for one movement. This one is combined. Okay. And then you see some of the arrows are dashed, some of them are solid. Solid is what we call as protected. Written somewhere. A solid line indicates protected movement. Protected means what? It happens with the signal. Okay, it happens with the signal. Permitted means what? So the other one, the dotted one, is called permitted. Permitted means what? It depends upon the clearance of the intersection, not the signal. Okay, so if I am going in a permitted direction, I will go through it if the intersection is clear. If I am going through a protected movement, I will not go just because the intersection is clear. If the signal is red. Got it? Clear? So this one is very common, right? Right hand, very common. Okay. This one, suicide. Okay. This one shows the 2 diagrams. The first one is the phase diagram. You can see movement from different directions are together. Okay. How many phases we have? 2 phases, because in the phase diagram you see 2 sets, right? Clear now? Then we have the ring diagram where the sets are separated according to their directions. Okay. Now, obviously, this means what? These 2 are, the dotted ones are what? Permitted. Okay. So this can only happen in this way. Okay. We have only 2 phases for a 4-way intersection. It can only happen in this way. Okay. Then you have this one. Now what's the change here? How many phases first of all? 8. Okay. Which phase did we add? Phase for what? There were 2 earlier, right?
Yes.
So which one did you get? Huh?
The middle one is the extra.
The middle one is the extra one. What did you separate from those two phases?
That one.
This one. Which one? Which one changed?
The first one extra.
This was it. Two phases. Then you change into these three.
The first row.
This one?
No.
Oh.
No, I was looking at this one.
This one? Okay, same. Same, right? Okay. The left turning was there. And what happened to the intersection itself?
More conflict points.
Huh?
More conflict points.
More counter points. When we added the third phase, we changed the intersection as well. What did we change? Yes?
More like time.
Yes.
Stick.
No straight.
The geometry we have.
High one.
We added the split plane.
There's another high. I have only one high. Now, another high. Yes. Yes, tell me. Yes, you are right. Which one?
We added the split plane.
Slip lane. You mean this one, right?
Yeah.
This is.
It's not split plane. It's not a split plane.
Okay. So we had to add the lane because the separate left turn cannot happen without separate lane. Okay, so we had to. If you keep this one lane in each direction and try to add a separate phase for left turn, it will not work. Okay, so now you see the changes in intersection geometry because of the changes in phasing plan. Okay. And the interesting thing is, it is written on the slide what changed. You guys will not read the slide even if I am showing you. Right? And then you ask me at the time of exam, should we only read from the slide? Yes, like you have been doing the whole semester. Okay, what changed here? Yes. Yes, what is it? Explosive pedestrian phase. Okay, so this thing. You don't see any arrows here because no movements allowed. Okay, I saw these type of signals in Europe, and you can like close it yourself. Okay, you go there, like we do, like a pedestrian push button.
Press.
Yes.
Go.
Okay.
Then press again to get make one.
You don't press again.
I didn't.
You keep on pressing.
No, I didn't.
Press from here and go and press again.
They press, and when they reach the other island, they press. I thought that they press again. The pedestrian.
You thought you don't do it, right?
No.
Okay. So they do that. Okay. With the pressing here we have those press signals mainly at the roads, not in the intersection. So there's only one direction which you stop. Okay. Here they have it on the intersections, and some of the intersections are like one-way streets. So two one-way streets are crossing. This is a one-way street. This is a one-way street. Okay. So when you stop, they stop all of them. All of them stop. All streets are closed. Okay. So you just go, and that also means that they are very, very short. Okay, especially for people like those guys are fit. They don't go from one class to another class on car. So they are fast. They are used to walking. Okay, so nothing. Okay. Moving on. The next stage is for calculating timings for the vehicles. The first type of timing calculated is yellow and orange. Okay. Other name for yellow is change interval. Another name for orange is clearance interval. Okay. Now keep in mind, there is a clearance loss time and there is a clearance interval. They are different. When we say loss time, it is for the drivers from the driver's perspective. Okay, lost time is from the driver's perspective. When we say interval, this is something related to the signal. Okay, so when I say clearance interval, I am talking about the timing of the signal. When I say clearance lost time, I am talking about the time which the driver is doing something. Alright, so they are different. Their values are different. Okay, so here we are talking about clearance interval, not lost time. Okay, so on the right hand side you see the equation for yellow or change interval. On the right hand side you see the interval for red. The yellow equation, it is basically coming from the equation of stopping side distance. Okay, so the equation of stopping side distance gives you what? It gives you distance, right? Okay, if I want time using distance, I need what? Speed, 85th percentile, right? So, yes, we need 85th percentile. Okay, so they took the equation of stopping side distance divided by the speed. So that gives you time. Okay, so we have perception reaction time for the vehicles. We have the acceleration, the deceleration, normal one. We have the capital G, which is what? Rate. Okay, and the 85th percentile speed. Then you move on to the other side, which is for all red time. All red time can have 3 cases. Okay, you have to pick one of the cases, and these cases depend upon pedestrian volume. Okay, the pedestrian volume is non-existent; it is not available or it is not allowed. So there are no pedestrians crossing there. Okay, so in that case, you will use the first equation to calculate the order time. Okay, if the pedestrian volume is very high, maybe in a market area or something, then you use the second equation. Okay, and if it is not very low and very high, something moderate, you will use this equation. Okay, and this equation you have 2 terms. Okay, and this one here the comma. So comma, and then you have this one. So it means what? Either this or this. They are not multiplication. Okay, they are not multiplied. You have to pick one of the ratios. Okay, now what are we showing here? The first thing is W. W means the width of the intersection. Width of the intersection. Okay, so the width the car has to cross, and it could be different for each direction, right? I could be crossing in this direction, or I could be crossing in the cross direction. Okay, so this width may not be equal to this one. Okay, so it could be different for each phase, and it could be different for each movement as well. Okay, we said that we calculate everything for what? All these timings are for what? On the basis of what? Which volume? In the critical, peak, critical, everything is correct. Yes. Peak volume, but for the critical lane, and that critical lane would be left turning. So then the width of the intersection is not this. It's this. Okay, the whole path. Okay. So this depends upon movement and the intersection size. Then we have L, which is the length of the normal car. Okay, taken as 18 to 20 feet. And then we have what else? P. P is the distance from your side to the opposite side pedestrian crossing. Okay, so W is from your side to the other side for a car. Okay, and P is from your side, this stop line, to the crosswalk on the other side. And the crosswalk and the stop line are not the same. Okay, crosswalk is usually after the stop line. If I am going like this, I will have the crosswalk first and then the stop line. Got it? Okay, so this is what it means, and here we are using 15th percentile speed. It's still for the vehicles. Okay, it's still for the vehicles. So here we are using 85th percentile here, and at the other side we are using 15th percentile. If they have given us some approximation as well if you don't have the full speed data. Okay, to get the percentiles, if you remember, you should remember, all of you like plotted the spot speed curves. All of you did. I didn't ask anyone, but all of you did. I don't know why. Okay. So you plot the curve and then you get the 15 percentile, 85th percentile. So you need the whole curve for that. Okay. So let's say you don't have the full data. Okay. For example, in your senior you got what? The values, right? Nobody gave the full data. Okay. So if you have that scenario, then you have to use 15 percentile, 85th percentile. Then you can do it from the mean. Okay, and do it from the mean. This is to show you what W and P means. So stop line to stop line is W, stop line to crosswalk is P. Okay, small example, we have to find out the change and clearance interval. Change interval means what? Which time? Yellow time. Okay, and the clearance is the all red time. They have given us the speed, average speed. The gradient is given. Distance from stop line to the other lane is given. Now, which distance is this? Is this P or W? P. P.
I don't know.
This is from the stop line to the other lane.
There's distances for that radius and the second for the distance.
Okay, so first one is W. Okay, very easy way to remember is pedestrian P. Okay. Then we have the standard length of the car, the reaction time, the deceleration rate, and there are some pedestrians present. Okay, let us start first of all from the yellow time. Yellow time requires these things. Okay, so perception reaction time is given. How much is that? 1 second. Okay, for the signals it is usually low. What is the normal one? 2.1. Yes. Okay, that is why the car is moving. That's the signal. Okay, then I need the A value is given here, somewhere, not given. 10. The A value? 10. Okay. Again, because it's a signal. The normal one is higher. The normal A value is higher. Gradient is given how much? Minus 2.5. Minus means upward number. Okay. 85th percentile speed. 85th percentile speed is not given. We are given with the average speed, and then the relationship between the 85th and average is +5. Okay. So how much is the yellow time? 3.5. No? 3.9. If it's a design problem, I will round up. Okay? No? Yes, I don't have. Okay. Clear?
Yes.
Any question? I'm asking you. Aisha. Aisha, right? Any question? We need 85th percentile. Why do what? Ah, sorry. It is 40. Okay, yellow time done. Now we have to calculate the alternate time. They said in the question some prediction volume. Okay, and then you can imagine the words which we can use for sum. We can use moderate. We can use okay, anything which is not very high or very low. Okay, that is some prediction volume. So in this case, I have to use one of these ratios. Okay, so my AR can be the first ratio or the second ratio. Okay, now what are the things we have? W. Remember, they are just doing it for one approach. So W is whatever they gave. What did they give me? 48. Plus the card length divided by the 15th percentile speed, right? Okay, again I have the average, okay, and I need the 15th percentile. So the relationship is minus 5. Okay, it can be this one or it can be the other one where P is 60 and the same thing here. 1 point how much and how much?
1.5 and 1.4.
This is 1.5?
Yes.
Clear? What will be my final value? 1.5 or 1.4? 1.5. Okay, any questions? Any problems? Clear? Okay. The next thing which we need is lost time. Lost time is observed from the field. Okay, so there are studies which I done to find out the lost time. We have discussed it earlier. I believe it was part of online class. I don't remember exactly, but we have discussed it was part of the previous section. Okay, so you need to observe, like you need to perform a field study to find out the actual lost time. But obviously, every single design may not give you enough opportunity to do these studies. Okay, so there are some recommended values given here. Okay, so for the startup loss time is 2 seconds per phase. Startup. Okay, startup is when the signal becomes green. Okay, the loss time when the signal becomes green. So the driver is still getting ready. Okay, so that loss time. And just keep one thing in mind. And we say 2 seconds per phase, it is not per driver. Okay, so like if there are 3 drivers, so it's not 2 seconds and 2 seconds and 2 seconds. It's like 2 seconds for complete, all of them. Okay, maybe this one took half a second more, this one took 1 second more. Add it. Okay, it only happens for the first 3-4 drivers. Okay, others are ready. Super ready. Ready than the driver who's in the front. Always more ready. The guy who is at the back of the queue is always more ready. Okay. Then we have the clearance loss time. Okay. Again, reminder, clearance loss time, not clearance interval. If I said clearance interval, what do I mean? Which time? Red time?
For the signal.
For signal?
And the span for the driver.
Are we calling it red time? What did we call it here? We were calculating clearance interval. Right? Did we call it red time? What did we call it? is clearance interval. The other name is what? Which interval?
Stop.
The change is yellow. So yellow has two names, right? Yellow interval, change interval. Clearance also has two names, clearance interval and red time. Is it red? It is green. It's all red. So there is a difference between all red and red. Okay? There is all red and there is red.
Clearance is the order.
All. Okay? Like if I give 0 to everybody, then all of you will become red. That all. Okay? Okay, so all red means all signals are red. Okay? All directions are red. This is why this is for clearance. Okay? Because we are clearing what intersection. So for this. So all signals must be red. Okay? So after all red, one of the directions will start green. The other directions are still having red. Okay? So all red is very small interval. But you know red is your whole life, right? Feels like, right? Yes? No? Huh? Okay. Now the point is, I told you clearance interval and clearance loss time are not same. Okay. Okay, why they are not same? No, I said clearance interval and clearance loss time are not same. I didn't say all red and red.
Okay.
Okay. The difference between them is the last part of yellow. Okay. Clearance interval is just all red time. Clearance interval is just all red time. Clearance loss time also includes the last part of yellow. So before all red it is yellow, right? Okay. So the last part of yellow is also counted under clearance interval. Okay. Because we are assuming, or some people in some other part of the world are assuming, that drivers may stop or may think that it's yellow or will not cross. Some drivers. Okay. We still have to find them. Where are they? Okay. But definitely not here. Okay. So, and obviously to keep a factor of safety. Okay. So we are taking the loss time, clearance loss time more than the all red time. This is like a factor of safety. The last 1 second of yellow are like the factor of safety. Okay. For the extra 2 on the safe side. Okay. So this is the difference between them. Again, they have given us a value. Okay. But the value is given for the total loss time, which is considered as the value is given for the yellow, which is counted under clearance. Okay, so this is 2 seconds. Okay, or the yellow which is not counted, the yellow which is not counted under clearance, that is 2 seconds. Okay, so for example, in this example, you calculated yellow time to be 3.9. Obviously, you will not design 3.9. You will design what? 4. Okay, so from the 4 seconds of total yellow, the usable 4 seconds are 2. Okay, the remaining goes under clearance loss time. Okay, so clearance loss time is whatever is remaining of yellow after 2 seconds plus all red. Okay, clearance loss time is the remaining part of yellow after 2 seconds and plus all red time. Now this 2 is a recommended value. I told you earlier this lost time and this time is the recommended value. Otherwise, we will do studies to find out how much time the drivers are actually losing. Okay. So in the previous example, there may be some rounding off issues here. Okay. So we got almost 4 seconds, and then we have 1.5 seconds off already. So 4.2 plus 1.5. This is your whole interval. From there, I will deduct how much? 2. Okay, so 4.2 plus 1.5 minus 2 will give you the clearance loss time. Alright? Clear? Okay. And the startup loss time is also 2. Recommended one. Okay. So if you are using the recommended values, what will happen? So this is where they went smart. They said we are subtracting how much here? 2. And we will add how much? We'll have the same value. Okay. But obviously for all countries, for all types of drivers, the values are not 2 and 2. Okay. So this balancing may not happen every time. But anyways, according to their logic, according to their values, you will subtract 2 seconds to get the clearance loss time, and then you will add 2 seconds more from the startup to get the total loss time. The total loss time, according to them, is the same value which is this one. Got it? Clear? Okay. The next thing which we do is you find out the critical lanes. Okay, so you have the phasing plan, you look at the phasing plan, which lanes will go in each phasing plan, you look at their volumes and you find out which one is a critical volume. Now we discussed critical volumes earlier as well. We have 2 lanes. Okay, how do we decide which volume is critical? The one which is what? If I have 2 values, I look at need more time, yes. And the more time can depend upon the type of movement as well as the number of values. Okay, so your critical lane volume, and it can also depend upon the gradient. The gradients are different, and you are looking for different approaches. Okay, and like we have seen earlier, there can be overlapping movements. You can have one from this direction, one from the other direction as well. Okay, so still you have to pick one. Got it? There. Sure. Okay. Now we already know if we have heavy vehicles, how to convert heavy vehicles into passenger cars. You already know that, right? You like 2 is speed. We did that. We converted heavy vehicles into passenger cars. Yeah. You did that. You presented it last time. The speed, see? We love speed curves. Even if the doctor is not asking, you will make 3-4 speed curves. Yes. But not the speed curves. Speed curve has nothing to do with heavy vehicles. Yes. What did you do in the LOS calculation to convert the heavy vehicles to passenger cars? What was the factor? Which factor? Heavy vehicles factor. Okay. Yes. Okay. So we know one type of conversion. Okay. That if you have heavy vehicles in this lane and this lane and this lane, we can convert all of them into passenger cars. Okay, with the use of heavy vehicles factor. But what if I have 100 passenger cars here, 100 passenger cars here, 100 passenger cars here, but this one is for turning. Okay. So yes, maybe this one had 2% trucks, this one had 3% trucks, this one has 10% trucks. Okay. So I could not compare between them. I converted all of them to passenger cars. So now I can compare. Okay. But now the new problem came that this one is turning. So although this is 100, this is 100, this is 100, but this 100 is turning. Okay. So how can I compare? Okay. So now I need another equivalency factor for turning. Okay. And in this case, our life is simple. There is no equation. Okay. Turning, we will use these tables. Okay. For left turning, we can use this one because our left turnings are protected. Okay, our left turnings are not permitted, right? Okay, we don't make the left turning if the intersection is clear. We still have to wait for the green, right? So our left turnings are, he is thinking, do I wait? No. We have to wait. Okay, so our left turnings are protected. So you can see the factor is lower. Look at these factors. Factor is lower because the risk is less. So the vehicles can go faster even if they are turning. Okay, but if you are making it permitted, I have to go with caution, right? Because the signal could be any signal. Okay, so I can see, yes, it is clear now. Maybe I start moving and then somebody comes at 100 kilometers per hour, right? So then the factor is higher because you are going slowly. Okay, so this one, in most of the cases, if you have a phase for left turning, you will take this factor. Okay, if you don't have it, then it depends upon this. You can see it depends upon number of opposing lanes and number of opposing volume. What opposing means, if I am taking the left turning from this direction, the opposing is the one which is coming conflicting with me. Okay, so this left turning will not conflict with the opposite left turning. I am turning here and this guy will turn in this direction. Both can go on our ways without any conflict. Okay, the opposing is, if this is the left turning, then this is the opposing. So we are talking about this volume and these lanes. Got it? Clear? Clear? Okay, for right turning, there is no opposing. Okay, but there could be pedestrian crossing. Okay, so that's why it depends upon pedestrian volume. Clear? Okay, but in each case, the factors are very they are fixed. Now what can we do with these factors? You take these factors, you multiply the turning volumes. Okay, so those turning volumes now become equal to straight volumes. Okay, they become equivalent straight volumes. The term used in signal design for straight is through. Okay, the term which they use is called as through volume. Okay, so through is straight. Right? Okay, so when we multiply the equivalency factor, the 100 turning left became whatever number straight. Okay, so if I have 3 lanes now, okay, this one for straight, this one for straight, this one for left turning. Okay, so I can compare between these two, but I cannot compare with this one until I take the equivalency factor. Okay, so once I multiply the equivalency factor, this is like straight, and this is straight, and this is straight. Now I can compare. Got it? Clear now? Okay. This is for one phase. Okay, so I design a phase for this direction. Okay, and this direction has left. The other direction, maybe the critical lane in the other direction is through. Okay, so this one critical is left turning one, and from the other phase, the critical one is the through one. Okay, when we are calculating the cycle length, we have to take critical from here and here and here and here, add them together. Okay, so without the equivalency factor, this addition is also not possible. Okay, you cannot simply add 100 left with 100 straight and say they are okay. Now they are 200. No, they are not 200 because those 100 are more than 100. Right? Okay. So after you do this, then you can do the addition as well for different phases. Now let's say we don't, let us look at one example which shows how these factors are calculated. Okay. So they are calculated on the basis of time. Okay. We said critical is the one which needs more time, right? So the equivalency factor also depends upon time. Okay. So compared to a through vehicle, a left turning will need how much more time? That is the equivalency factor. Okay, so how do we do that? We have an intersection which has two lanes. One lane is for through vehicle only. The other lane is through plus left combined. So what did they do? When the signal opened, they had vehicles in both lanes. They started the watch. Okay, and they looked at the watch for X number of seconds. So both lanes were open for X number of seconds. In those X number of seconds, so it's the same time for both lanes. Okay, in those seconds, the through vehicle passed 20 vehicles. Through lane passed 20 vehicles. From the other lane, in the same time, they passed 10 through and 5 left turning in the same time. Okay, so I had how many here? 20. And how many here? 10. Yeah. So I cannot say 15 here. Because 10 are straight and 5 are left turning. Okay. So what do we do? If I have to calculate the flow, 20 straight divided by time x equals same time, right? 10 straight time same plus 5, but they are not straight, so they must be multiplied by the equals. Correct? So now this is gone. We can calculate the equals. Correct? How much is it? Two. Yes. In the same way, you can do it for different combinations. Okay. Okay. So in this example, again, a very small one, the equivalency factor is here, 2.7. So according to the intersection geometry, the equivalency factor for left turning is 2.7. They counted total volume. Okay. And they found the percentage of left turning meters, like what you did in your term project for the head. You found the percentage, right? So they did the same thing for the left turning. So they found the percentage to be 8% for left turning out of the 1,050 total meters. Okay? But the problem with this number is that those 8% left turning and the remaining are just added, which is wrong. I need to add them in equal terms. Before adding, I need to bring them in equal terms, which is not done. Okay, so what should I do? First of all, I will find out what is my left turning volume. My left turning volume is 8% of 1350. Which is how much? 100. These must be multiplied by the equivalency factor. So they will become equal to through. Okay, which is how much? 2. Yeah. Okay. Now I need to add them with the through vehicles to get the total number. How many through vehicles I have? Minus 150. Okay. It was 1350, from which this was left turning. So I will subtract them to get the straight ones, which is what? 1, 2, 4, 2, right? And now I will add this to get the total. This is the true total. Which is how much? 1,534. Okay. So if this was a total volume on an intersection, 1,350 will be the wrong value. the correct value will be 1524. Okay. Okay. In this example, they have already done the conversions. All the conversions are done. Everything is pressing the car, everything is 2D. So I can add them, I can compare them, no problem. Okay? First of all, how many phases we have? 3. Why? Because it's A1, A2, A3, right? And everybody needs an A. Yes? 4. You counted what? Huh? You counted the lines, right?
No, for the phase graph, it is 3.
Huh?
Isn't that ring versus phase map or graph?
This is ring diagram.
Okay, fully ring.
Yes.
I thought that was phase map.
See how this is how I get ideas for final exam. So I don't make final exam at the end. Yes.
Why not 3?
Why not 3? Because you said 4. We are following you. Okay, here are 4 phases. A1, A2, A3, and B. 4 phases. Okay. Now phase is what? Phase is the time during which same movements are allowed without change. Okay. So what happened in A1? These 2 movements are allowed. Okay. Then at the end of A1, at least one of them is stopped. At least one of them is stopped. So the next phase has started. Okay. You cannot stop or start a movement in the middle of the phase. So whenever you start or stop a new movement, any new movement, then it's the end of one phase and you go to the next phase. Okay. So here you see one movement. Out of the 2, one ended and one began. The other one is still going on. But even if one changed, it's a new phase. Okay. Same thing at the end of A2. This one stopped, this one continued. But because this is stopped, it's a new phase. Clear? Clear? Okay. So we have 4 phases. For each phase, they have, not each phase, for each movement, they have given us the volume. And the volume is all equal terms. Okay. So you can now compare directly. What we have to do is find out the critical volume here. Total critical volume. Total critical volume. So I'll look at each phase because there are multiple movements in each phase. And I'll pick one of them as my critical volume. Okay. We start from the bottom. Phase B. This one and that one. We have how many lanes in each direction? Lanes. One lane. Shared movement, right? That one lane is sharing the movement. Okay. So you have 300 on one side from one lane, 280 on the other side. Which one is critical? 200 because they are equal now. Okay. So I can safely say 300 is a critical now. Okay. Phase B decided. So now I move to A3. This one and this one. 600. But 600 goes up to here. So 600 is not for A3. 550 because
It only goes for one piece. This is the share, A2 shares.
Okay. A2
The 600.
the 600 is here. Here 300. Where's 300?
This is 600 divided by 3.
600 okay. It may not be. Yeah, yes. Okay. In this case, we look at the sequence, the whole sequence. We take the whole sequence as critical. Now, sequence means what? Movements which are conflicting with each other, they have to be in a sequence, right? For example, this and this, they have to be sequence. Can I make them together? Can I make them together? You think yes. You did this well, right? Can this one and this one happen together? No. So they have to be in one sequence, order, one after the other. Okay? So I look at this order and I find what? 150 plus 600. Total? 7. Okay? So one sequence, one order gives me 750. If I look at the other side, again, they cannot happen together. Okay? So 550 plus 250. This order gives me what? 800. Right now, I am just interested in total. So should I take this total or this total? I will take this one. I am not assigning time for each phase yet. Remember. I am just trying to find out the total volume which I can use for calculating cycle length. Clear or not? Okay. So for this one, I pick this one, very easy. From this one, I pick this one. Okay. So 800 from there, 300 from there. Total 1000. Okay. Then we can calculate the cycle length. This is where we will stop today. Okay. So this is the equation of cycle length. We have used it earlier as well. How many phases we have? 4 phases. Lost time per phase is given here. Per phase. Okay. And this is also per phase. Important point for the exam as well. What people do is they take per phase value. We have 4 phases, multiply, and then put it here. Equation is multiplying itself. You don't need to do it. Another problem, this is total lost time. Total lost time has 2 parts. Okay. Startup lost time, yes. You put the total here. Okay. But total for one phase only. Got it? Okay. What else do we need? We need saturation headway, given. We need peak hour factor, given. We need D/C ratio, given. Okay. Number of phases are coming from the diagram, and GC is the total volume which we have taken. 1100. Clear enough? Any questions? Any problems? Okay.